Recent images captured by the James Webb Space Telescope have shocked experts, revealing an unsettling truth. Instead of enhancing our understanding of the universe, these images suggest that our current physical theories may be insufficient to fully comprehend the universe, particularly in its early stages, where the Big Bang theory reaches its limits. This discovery forces scientists to reconsider new theories about the origin of the universe. A critical question now emerges. How exactly did the universe form? And why do these new findings challenge even the most seasoned astrophysicists' understanding of the Big Bang? Let's revisit the concept of the Big Bang. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Instead, it was the moment space itself began about 13.8 billion years ago, along with matter and time. This phenomenon is referred to as a singularity in physics and astronomy, a point where gravity is so intense that the curvature of spacetime becomes infinite. Today, after billions of years since the universe's beginning, we observe that our infinite home is part of an ongoing process. For scientists, this reflects a fundamental characteristic of the universe since its inception: seemingly perpetual expansion. It's important to note that the universe is not expanding into pre-existing space. Rather, space itself is continuously growing. According to current theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first luminous celestial objects began to form into mature galaxies. However, the rate at which these galaxies developed remains a significant mystery. In July 2022, new data from the James Webb Space Telescope revealed several galaxies, some of which had already existed about 300 million years after the universe's birth. These early galaxies, compared to those that formed later, were considerably smaller and less massive. This aligns with a scientific model, which suggests that the matter density in the early universe was insufficient to form galaxies as large as those observed today. What began as the discovery of 6 distant red-shifted light sources from the James Webb Telescope soon became one of the most significant cosmic puzzles of recent times. These galaxies, although comparable in age to previously recorded ones, were nearly as large as our Milky Way galaxy. This has sparked an intriguing conundrum in galactic research. By analyzing the series of images captured by Webb's near-infrared camera, scientists identified these distant light sources. Using redshift, researchers calculated that the light from these objects traveled over 13 billion years to reach Earth. This means we are observing galaxies that had already existed around 500 to 700 million years after the Big Bang. Surprisingly, these galaxies were so massive that they defied traditional cosmological expectations. Instead of finding the expected smaller dwarf galaxies, astronomers discovered structures nearly as large as the Milky Way, despite forming so early in cosmic history. If further analysis confirms this, it would suggest a much higher concentration of matter in the early universe than previously thought. This discovery contradicts nearly all standard cosmological models. Even if only one of these galaxies turns out to be real, it would challenge our understanding of galaxy formation and the conditions required for such structures to arise so early. For one, the matter density in the early universe would have to have been much higher than originally theorized to explain these gigantic early galaxies. Another possibility is that these galaxies formed in ways that are still completely unknown to us. This new discovery, coupled with debates surrounding the Big Bang theory, is driving more astronomers to reconsider this long-held explanation for the universe's origin. Some scientists are exploring alternative hypotheses, questioning whether the Big Bang theory is sufficient to explain everything we observe. There are many unresolved questions, even among those who still support the Big Bang theory. For instance, how did the universe emerge from nothing 13.8 billion years ago? Was there some triggering event, or was it all a cosmic coincidence? Physicist Stephen Hawking pointed out that the nature of time as we understand it began only with the Big Bang, so this event could not have been triggered by anything prior to it. One controversial issue is the consistency of radiation throughout the universe. Regardless of direction or distance, we observe similar densities of galaxies, nebulae, and radiation across the cosmos. Researchers explain this by the theory of cosmic inflation. However, some take this theory further, suggesting a model of turbulent inflation, where inflation may have stopped in some regions, forming bubbles, while continuing indefinitely in others. This would imply the existence of multiple universes, each with its own set of physical laws. A fundamental question in this framework is, what if our universe is not the only one? If another universe existed before ours, the Big Bang might be just a part of a larger cyclical process. In this view, our universe could be part of a grander structure, undergoing a continuous cycle of collapse and rebirth. This model supports the idea of a universe that perpetually regenerates itself. Moreover, alternative hypotheses have been proposed. For instance, in 1955, an article published in NASA's Astronomical Times argued that there may never have been a Big Bang, suggesting that the universe could have existed for an infinite amount of time. In this view, the expansion of the universe is an illusion created by the continuous formation of matter. Another intriguing theory comes from the realms of quantum physics and string theory. Some studies suggest that the visible universe may simply be a projection on a higher dimensional brane. In this scenario, everything we observe could be a lower-dimensional image of a more complex higher-dimensional reality. This idea, though reminiscent of science fiction, is linked to the Kardashev scale, which measures the technological advancement of civilizations. These recent findings, along with emerging alternative theories, present a profound challenge to our current understanding of the universe's origins and evolution. The shocking discoveries made by the James Webb Space Telescope have certainly altered the course of astronomical research, leaving scientists with more questions than answers. As we continue to analyze these findings, the mysteries of the cosmos may require entirely new frameworks to explain. The idea that our universe could simply be one bubble among countless others, each with its own distinct properties, challenges us to find observational evidence to support such theoretical concepts. These theories stretch the limits of experimental verification. Another thought-provoking hypothesis suggests that our universe might exist within a simulated reality, akin to a computer-generated simulation. This idea draws parallels with advancements in artificial intelligence and computational science, where simulations can recreate complex systems with remarkable precision. If this is true, it would radically alter our understanding of reality, raising profound philosophical and scientific questions about the nature of existence. Meanwhile, progress in observational astronomy continues to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, are expected to uncover even more of the universe's mysteries. Future observations may offer insights into the earliest moments of the universe, providing clues to its ultimate fate and the fundamental laws that govern its evolution. Beyond astronomy, particle physicists are delving into the essential particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Concepts such as quantum gravity and string theory offer potential frameworks for understanding these key interactions on both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself is subject to intense debate. The traditional view of time as a linear progression from past to future is challenged by quantum theories suggesting that time may be emergent or even illusory at its core. Understanding time in the context of cosmological models could fundamentally change how we perceive the origin and development of the universe. Furthermore, the search for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope study of exoplanet atmospheres, could provide evidence of biosignatures indicative of life beyond Earth. In addition, scientific endeavors and philosophical reflections on the universe deepen our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration spark ongoing debate and research across various disciplines. As we stand on the precipice of a new era in astronomy and cosmology, fueled by technological advances and theoretical breakthroughs, we are reminded of the profound interconnectedness of all things, from the smallest subatomic particles to the vast cosmic structures spanning billions of light-years. The universe slowly reveals its secrets to those who dare to explore and question. In conclusion, the study of the universe and its origins is a journey that transcends disciplinary boundaries, challenging our fundamental assumptions about reality. Discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and raise new questions about its evolution. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic expansion, we draw closer to a more comprehensive understanding of the universe and our place within it. Through collaboration between astronomers, physicists, philosophers, and technologists, we embark on a collective mission to decode the vast cosmic code, an endeavor that promises to redefine our understanding of existence itself. Whether exploring the depths of black holes, tracing the paths of distant galaxies, or contemplating the nature of being, each revelation brings us closer to unraveling the intricate tapestry of the universe. As we venture deeper into the cosmos, driven by curiosity and a desire to understand the boundlessness and complexity of the universe, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers. As Albert Einstein once said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." In our quest to confront the universe's mysteries, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the cosmos and ourselves. Thus, the exploration of the universe is not merely a scientific endeavor but a profound human pursuit of knowledge and meaning, a journey that transcends the boundaries of space and time, urging us to reflect on our place in the grand tapestry of existence. The advancement of a civilization is closely linked to its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the energy of an entire galaxy, it might have created an astounding simulation. However, understanding the reality of such a situation is highly complex. Delving into the depths of cosmology and the origins of our universe brings us to a realm of profound mystery and ongoing scientific inquiry. The recent images captured by the James Webb Space Telescope have reignited discussions about the very fabric of our reality. These findings challenge established theories and urge scientists to reassess core aspects of cosmological understanding. Central to this investigation is the Big Bang theory, a cornerstone of modern cosmology. According to this theory, about 13.8 billion years ago, the universe emerged from an extremely dense and hot state, expanding rapidly and giving rise to space, time, and matter as we know them today. This cosmic event was not just an explosion within pre-existing space, but also the creation of space itself. The concept of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early epoch. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structure began to form in the universe's infancy. These galaxies, identified just a few 100 million years after the Big Bang, appear unexpectedly mature and massive, contrary to predictions based on current cosmological models. One of the key questions raised by these discoveries concerns the nature of cosmic inflation. According to the prevailing theory, inflation occurred in the first fractions of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion is thought to explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the new findings suggest that the early universe's evolution may have been more complex than previously thought, potentially requiring revisions to inflationary models. The formation of galaxies, such as those observed by the James Webb Telescope, raises further questions about the density of matter in the early universe. These galaxies, which are significantly larger and more massive than expected so soon after the Big Bang, imply a matter density that exceeds earlier estimates. This mystery deepens when considering how such massive structures could have formed and evolved in such a short period of cosmic time. Additionally, the discovery of these early galaxies brings up intriguing questions about dark matter and dark energy, two elusive components that constitute the majority of the universe's mass energy content. While dark matter is thought to provide the gravitational framework essential for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In light of these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the traditional Big Bang framework. Some theories suggest that our universe is just one of many in a vast multiverse, each with its own distinct physical laws and constants. These ideas, stemming from developments in string theory and quantum cosmology, propose a more intricate and interconnected universe than previously imagined. One concept gaining traction is eternal inflation, which suggests that new universes continually arise from a larger, ever-expanding space. This theory proposes a universe far more complex and dynamic than the standard Big Bang model, offering new perspectives on the origin and nature of everything we observe.